about the basics of the compound angle stuff, dealing with, come on, oh, maybe it'll work. There we go. I'm dealing with finding the length of the path and then the angle of rotation and the angle of tilt to line up those boxes corner to corner. So today we're going to look at drilling. And this is really the same calculation as what we had yesterday. It's just a matter of setting it up. So we're going to be looking at a piece of material from a top view where we have an entry hole at the top of the part and the exit hole from that bore on the bottom of the part. And of course the part, if we're looking at it, is going to have a thickness. Let me draw it. She'll draw it like this. The end view of the part here, entry hole, exit hole, it's going to look something like that. Front view of the part, entry hole, exit hole, it's going to look something like that. So we can see basically what we're looking at here is creating that box from these dimensions, from this setup that we had yesterday. So we're going to go center to center on the hole. This will be that rectangle created by using those centers as opposite corners. Is basically going to be the top surface of that box that we worked on yesterday. So let's say that this is 0.8 inches here and 0.7 inches here. The height of the box, the depth of the box, is the thickness of our part. So let's say this is 1.1 inch here. So from this, we can create that box we were working with. Maybe. So something like that. And our path of our bore is going from this back corner, the upper back corner, to that lower front corner like that. This dimension here, this is the 0.8, the 0.7, and this is the 1.1. So let's find the length of the bore. We did this yesterday. That is that three-dimensional Pythagorean theorem. So the square root of 0.8 squared, 0.7 squared, plus 1.1 inch squared. Giving us 1.530. There's the length of our bore. So that's that green line, the length of that green line. We're going to come back to using that again later. Next, we want to find the angle of rotation. So if we're looking at the bottom of this, the angle of rotation is that angle right there. Again, if we're looking at it from the top, this is 0.8, this is 0.7. Our bore is going corner to corner across here. R, that's the angle that, this would be the dimension that's normally lined up side to side on the table of the press. We have to rotate it that far so that this line is now lined up side to side on the press. Find that angle, we're looking at this green triangle here. We have the opposite side, the 0.7, and the adjacent side, the 0.8. So R is going to be an inverse tangent. 0.7 over 0.8. Giving us, oops, gotta set my modes again here correctly. Giving us 41.19 degrees. So we would rotate that part 41.19 degrees on the table to line that path of the cut up side to side on our press table. Next, we need to know how far we need to tilt the table. If our table starts out like this with the part sitting on it here, even once it's properly rotated, so that path is angling like that, we have to tilt that whole table so that that bore is straight up and down. I didn't quite get it straight up and down there yet. So we have to get that table tilted so that when the drill press comes down, it will go straight through that bore. That's our angle of tilt. Of course, this here is that angle of tilt. On the part, where that would be is this angle up here between the actual bore and that vertical corner there back there. So that gives us a triangle that looks like this. We know this is the thickness of the part, 1.1 inch. And we know this is the length of our bore here, 1.530 inches. And we're looking for this angle is our angle of tilt. Because this would be straight up and down with the cables left flat. We want to tilt it so that now this is straight up and down. So the tilt there, we have the adjacent side and the hypotenuse. That's dealing with the cosine. So that angle of cosine is angle of tilt is the inverse cosine of the 1.10 divided by 1.530. So 44.03 degrees. Now, when I look at these angles, I want to, first of all, think to myself, ask myself, do they make sense? And if I go back to this original box that I drew, these dimensions are all pretty close to the same size, especially the 0.8 and the 0.7. So it makes sense that this angle of rotation here is going to be really close to 45 degrees, because a 45-degree triangle would have the two legs the same. 41.19 is a pretty reasonable size there. If I look at this triangle here, the 1.1 is just the height. But remember, we could have found this length here, which is the diagonal length. That would actually be this length here, across the bottom. If I found that diagonal length, which we don't need, but I'll find it here just to prove a point, we get about 1.06, really close to 1.1. So those sides are really close to being the same. So again, it makes sense that this angle of tilt is close to 45 degrees. So because the three dimensions in this box are pretty close to being the same, it makes sense that we get angles that are close to 45 degrees. So if I'm looking at a situation like this, Come on. And I am going to call this dimension here my length. This is my width, and this is my height or thickness. Our angle of rotation, as we've seen, is this angle here across the bottom. So that angle is just the inverse tangent. The opposite side would be the width. The adjacent side would be the length. So just W over L. The length of our bore we found is the square root of L squared plus W squared plus H squared, using that three-dimensional Pythagorean theorem. And our angle of tilt, of course, is this angle right here, T. We found using the adjacent side and the length of the bore, the hypotenuse, that's an inverse cosine that we used, is the adjacent side is the height divided by the length of the bore. Now, I don't memorize those formulas. I tend to just use them and apply them. We will look tomorrow, actually. There is a way, if you are given the front view and the side view here, rather than being given the length, width, and height of the part, you might be given this angle here that bore takes away from being straight or perpendicular to the part. And you might be given this angle here. And those angles can be used to find all this information as well, the rotation, tilt, and length of bore. We'll look at that tomorrow. For now, I want to look at least one more example here. My technical issues are holding out, so I'll keep going for a while. What happens when the orientation is slightly different from what we've been looking at? So let's say that our entry hole is there and our exit is here. Now it's really the same problem, it's just going to look slightly different than what we've been working on. The box that we might draw here our bore is going to go from this corner to that corner now. Our rotation is still going to be this angle right here. So let's put some dimensions into this. Let's say that this dimension here is 0.6 inches. This dimension here we'll call 0.5 inches. And our thickness here, let's call it let's go 1.5 inches. What the heck? That makes this 1.5. This 0.5. Obviously, I didn't draw this to scale. And this 0.6. So our rotation is still just the inverse tangent of the 0.5 over the 0.6. Again, it's in a different corner than what we're used to seeing it, but it's still same concept using the same dimensions. Second tangent, 0.5 divided by 0.6. 39.81 degrees. That's my angle of rotation. Now my angle of tilt will be right here, but before I can find that, I have to have the length of my bore. Of course, that length is still just going to be the square root of 0.6 squared plus 0.5 squared plus 1.5 squared. Give us 1.691 inches. So we've got the length of the bore. We can then quickly find our angle of tilt. Remember, the angle of tilt is the inverse cosine of that height, the 1.5 inches, divided by the length of the bore, the 1.691. Now again, those numbers are relatively close to each other. I'm expecting an angle close to 45, probably closer, a little bit smaller, because the opposite, the hypotenuse here is still quite a bit longer. Actually, it's going to be quite a bit smaller because that's the hypotenuse. But let's take a look here. Inverse cosine of 1.5 divided by 1.691. We get 27.50. So yeah, it's not even close to 45. So I misguided that guess. 27.50 degrees. That's our angle of tilt. So that's telling us again on the drill press, looking at it from the top view, here's our part. We're drilling, our bore goes across it like that. We have to twist it here. This angle is going to be formed. I make an imaginary line parallel to this side. This angle is that 39.81 degrees. And then the tilt, if I look at my drill press table from the front, that's how far we have to tilt this. So the length of that bore ends up being vertical. This angle is at 27.50 degrees. Now, if we are looking at running a drill here at 200 RPM with a feed rate of 0.03 of an inch per revolution. Once this is set up and the drill makes contact with the material, our time to cut, or cut time, we're just going to put time here, time to drill the bore, is going to be, well, 200 RPMs times 0.033 inches per revolution. That gives us our advancement per minute. That's saying we go 0.6 inches per minute. If I multiply that all out, I get 0.6. That's saying every minute that drill can go 0.6 of an inch into the material. Well, the length of our bore is 1.691 inches. We're going to take 1.691 inches divided by that to give us 2.82 basically minutes of cut time. Now I can do that conversion just like I would with feet, inches, and sixteenths or whatever. I can pull that 2 off there. That's 2 minutes. And I can take that 0.81 times 60 to get 49.1 seconds. So we're just going to call it 50 seconds. So once the bit makes contact with the surface of that metal, it's about just under 3 minutes time to drill that hole. However, we do have an issue from a practical side of this, an issue with drilling this hole. So here's our piece, and let's say the hole goes from here to here. We've got our rotation and our tilt all correctly done. And here's our drill bit coming in to drill that hole. What's going to happen when that bit hits the surface of that metal? It's going to want to deflect down that surface. Has Richard gone over it all with you? What is the maximum angle of bit to surface that you can have before you have to worry about deflection? You haven't talked about that at all yet? It depends on the type of drill bit and the type of material you're drilling into. But it really does not take much of an angle. It would be a good question to ask him to go over. In fact, if I think about it tomorrow, I'll try to track him down and ask him about it. If he has anything that he wants you guys to do. It's one of those things, I don't want to get too far into it because I don't want to tell you something different than what he would want you to know. But even a small angle like 9 or 10 degrees, that drill bit coming down into the material, when it hits the surface, it's going to want to slide down the surface and bend the drill bit like that. It's not going to, won't necessarily damage the bit, but it's going to deflect, and it's not going to enter the material where you want it to enter the material. So sometimes one of the possibilities that can be done is to lay the material flat and to drill a small hole, a guide hole. It has to be shallow enough so that when you come to drill the actual hole, that it doesn't deform the entry point of the hole. So you got to go in just enough to get the taper of the bit in there, but so that you don't go outside of that angle of the hole of the bore. So now when you come down, when the drill comes at the material, there's that little divot there already, and the drill hits that divot and it holds it in place as it enters the material. Like I said, I'll talk to Richard tomorrow and see if there's anything on that he wants you guys to know and see how he covers that. And we'll go over it later. For right now, you guys have homework. I got to find the page here. With all my technical difficulties, I didn't get all my lesson plans pulled up before I started this morning here. It'll be just a second. Still not sure why Blue Jeans isn't working on my main computer here. It's going to be out of that packet that I gave you. Well, it's posted online and the ones I gave you guys in the classroom last Wednesday. It is our next section on compound drilling. I'll have the page number here in just a second, hopefully. Maybe. There we go. So the page is 395 through 397. And there's problems 1 through 10 there. If you just want to do like 1 through 9, the odd, that should be more than adequate for these. Tomorrow we're going to move on then to a compound angular milling, which will leave us with Thursday morning being a quiz on the boring and milling. This Thursday morning, I'm going to be taking a personal hour, so I'll log into class. I'll be at home. I'll log in case there's any questions, but remind me tomorrow. I'll make sure I hand out that quiz for you so you have it for those of you in the classroom tomorrow for Thursday morning. With that, I'll let you guys get to work. I will end the recording here, and I'll be online if you guys have any questions.